And hello again from Fox News in Washington. Just as our parent network, we are fair and balanced. So after a very syntactic talk, we're gonna move straight to semantics and talk about higher categories. And our next speaker is Brendan Doherty from the University of Western Ontario, who will speak about cubical models of infinity one categories.
All right, thank you very much for the introduction, and thank you for inviting me. So today I'll be talking about this project I've been working on together with Chris Kapulkin, Zachery Lindsey, and Christian Sattler in, in categorical homotopy theory on cubical models of infinity one categories. So this is the main theorem that I'll be discussing today. We have this, this model structure which we've constructed on the category of cubical sets with connections, which presents the homotopy theory of infinity one categories, meaning specifically that it is Quillen equivalent to the Joyal model structure on simplicial sets, specifically via the triangulation functor. There's a lot of terminology there, which you may or may not be familiar with, but I'll be spending a fair bit of time today just going through some of the background involved in this statement and some of the necessary material there. So the reference that the new material I'm presenting today comes from is this paper that I've written here with Kapulkin, Lindsey, and Sattler on cubical models of infinity one categories, which is now on the arXiv. And many of the key results that we used in proving our theorems in this paper come from this paper by Kapulkin, Lindsey, and Wong on the co-reflection of cubical sets into simplicial sets. So those are the main references for this talk. Right, so to explain what's going on with this theorem, I should first review what a model structure on a category is. So this is a kind of structure which we can define on a bicomplete category, meaning a category with small limits and co-limits, which consists of a choice of three specified families of morphisms, what we call weak equivalences, cofibrations, and fibrations, which we indicate in writing with these special kinds of arrows that you see here. And these have to satisfy certain properties. So one, all three of these classes need to be closed under retracts. The weak equivalences need to satisfy the 2 out of 3 property. So that means if you have a commuting triangle in which 2 of the 3 maps are weak equivalences, then the third is as well. For every map in this category, we have to have 2 specific kinds of factorizations. So every map needs to factor as a map which is both a cofibration and a weak equivalence, or what we call a trivial cofibration, followed by a fibration. That's what you see here. And we also need to be able to factor any map as a cofibration, followed by a trivial fibration. And finally, if we have any commuting square, like we see here, where this map is a cofibration and this map is a fibration, and one of those 2 maps is also a weak equivalence, then there has to be a lift in this diagram. So that means there exists a map from this bottom left object to the top right object here, which would make both of the triangles that we would get commute. So if you do this and this, that's the same as just doing that horizontal map, for instance. So that may seem like kind of a technical definition, but the idea here is we can use these model categories to talk about different kinds of homotopy theory. Specifically, why this is important is that if given a model category M, we can construct the homotopy category of M, which we obtain by inverting the weak equivalences. But of course, when we do that, it's not immediately obvious that we would get a nice, well-behaved category. For instance, this may not be, like, it's not clear from this definition that what we get would be locally small, like a proper class of maps between some objects. So to understand the homotopy category, we can define certain distinguished classes of objects, which are very well behaved from the perspective of the homotopy theory. So we have what we call cofibrant objects. These are objects for which the map from the initial object in this category is a cofibration. And then we have fibrant objects defined similarly. These are those for which the map into the terminal object is a fibration. So these cofibrant and fibrant objects are the ones that are very homotopically well behaved in various senses that I'll talk a bit about. And these objects sort of capture all of the homotopy theory that's happening in a model category, in the sense that any object is weakly equivalent to one which is both cofibrant and fibrant. So we have these procedures that we call cofibrant replacement, where given any object X, we can get a weak equivalence into X from some cofibrant object. And likewise, we can do a fibrant replacement where we get a map from any object, which is a weak equivalence, into a fibrant object. And using the structure of a model category, we can define a notion of homotopy between morphisms. And one particular way in which these cofibrant and fibrant objects are well behaved is that this general concept of homotopy that we can define will be an equivalence relation on the set of maps from a cofibrant object into a fibrant object. And so using the general structure of a model category, we can develop a nicer characterization of these homotopy categories. So the homotopy category of M can be described as a certain quotient of the full subcategory on those objects which are both cofibrant and fibrant, namely the quotient where we quotient the set of morphisms by this equivalence relation of homotopy. Right, so a natural question to ask then is, how do we compare different model categories? What does it mean for two model categories to be equivalent, to present the same homotopy theory? So to do comparisons between model categories, we use certain kinds of adjunctions that we call Quillen adjunctions. So this is an adjunction between two model categories that satisfies two equivalent properties. So we can verify that either the left adjoint preserves cofibrations and also trivial cofibrations, or equivalently that the right adjoint preserves fibrations and trivial fibrations. So in verifying that something is a Quillen equivalence, we can choose to work with either the left adjoint or the right adjoint, depending on which one is easier to work with. And so an adjunction that satisfies this property, a Quillen adjunction, will induce an adjunction on the homotopy categories of these model categories, which we call the derived adjunction. And if that derived adjunction is an equivalence of categories, then we call this a Quillen equivalence. So let's look at some examples of model categories. One of the categories that we'll be looking at model structures on today is the category of simplicial sets. So I'll briefly go through a definition of what this category is. So simplicial sets are presheaves on what we call the simplex category, delta. That's this category whose objects are the posets 0 up to n for all n greater than or equal to 0. And the morphisms in simplex category are just what you'd expect. They're all order-preserving maps between these posets. So simplicial sets then are presheaves on this category, meaning contravariant functors into the category of sets. And we think of these intuitively as consisting of collections of simplices in all different dimensions, which are sort of joined together along common faces. So the value of one of these presheaves at the object corresponding to the poset n, we think of as the set of n simplices in that simplicial set. And we have these, for example, these simplicial sets that we call the standard simplices. These are the representable presheaves on this category. And these just resemble what you'd expect the n-dimensional simplices to be. So we have a 0 simplex, a 1 simplex, a 2 simplex, and a 3 simplex, and each of these simplicial sets contains all of their faces as well. So one of the most well-known examples of a model structure is this model structure that we have on the category of simplicial sets called the Quillen model structure. So in this, the cofibrations are the monomorphisms. The fibrant objects are specific simplicial sets that we call con-complexes, or infinity groupoids, and the weak equivalences are what we call weak homotopy equivalences. So to explain exactly what these things are, a con-complex is a simplicial set which satisfies a certain lifting property. So we have these special simplicial sets that we call the NK horns, lambda NK. These we obtain from the standard N simplex by removing the interior of the simplex and the K of face. So this property says that if you have one of these maps from an NK horn into X, it can be extended to a map from the standard simplex into X. Now, one context in which you may have encountered con-complexes in the past is Voevodsky's simplicial model of homotopy type theory. In that model, types are represented as con-complexes. And so, as with any model structure, there's a concept of homotopy in the Quillen model structure. So if we have two maps, say F and G from X to Y, then a homotopy from F to G is a map from delta 1 times X, so the standard 1 simplex, the product of that with X into Y, which restricts to these specific maps F and G at the endpoints of the interval. So the idea here is we're thinking of delta 1 as like an interval object, and then this product of delta 1 with X is like a cylinder on X. So from this, we can define a homotopy equivalence between con-complexes, because these are the objects that are well behaved with respect to homotopy, the fibrant objects. So that's a map that has what we would think of as a homotopy inverse, in other words, a map going back in the other direction from Y to X, such that these two composites are homotopic to the relevant identity maps. And from there, we extend that definition to define a weak homotopy equivalence between arbitrary simplicial sets, say K to L as we have it here, using these simplicial mapping spaces that we can define. So we have these simplicial sets X to the L and X to the K, which will be con-complexes if X is a con-complex. So we say this map K to L is a weak homotopy equivalence if for any con-complex X, this induced map on these mapping spaces is a homotopy equivalence. Right, so that's one example of a model structure on simplicial sets. Another one, which we can define as what's called the Joyal model structure. So in this model structure, the cofibrations are the monomorphisms again. The fibrant objects now are what we call quasi-categories, or infinity 1 categories. And the weak equivalences are what we call weak categorical equivalences. So the definition of a quasi-category is similar to the definition of a con-complex. It's, once again, based on having the right lifting property with respect to certain inclusions of horns into standard simplices. But in this case, it's not all horns that we require the lifting property against, but only what we call the inner horns, so lambda NK for K strictly in between 0 and N. So now to see what's going on with this definition, I've illustrated the inner horn, or the two-dimensional horns. So only one of these is inner, that's lambda 2, 1. And what you can see here is that this horn basically looks like a composable pair of morphisms, right? You've got these two edges where the target of one edge is the source of the other one. So for our quasi-category X to have the right lifting property against the inclusion of this horn into the two-dimensional simplex means that whenever you have a pair of edges like this in the simplicial set X, you can fill that out to obtain an edge from 0 to 2 and the interior of this 2 cube. So the idea then is we're thinking of that edge from 0 to 2 as a composite of this edge from 0 to 1 with this edge from 1 to 2, and the interior as like a homotopy that witnesses that composition. On the other hand, these other two horns really don't resemble a composable pair in any way, so we would not expect an arbitrary, cubical simplicial set that we're thinking of as an infinity one category to have fillers for these horns. If they did exist, that would essentially mean that any of these edges were invertible, which we would expect to see in an infinity groupoid, but not an infinity one category. Right, so in the Joyal model structure, again, we have a concept of homotopy, but it's not the same as the kind of homotopy that we deal with in the Quillen model structure. So to define the homotopies, whereas in the Quillen model structure we used delta 1 as an interval object, here we have this simplicial set that we call J. So this is supposed to represent an invertible edge. So the idea here is we've got this diagonal edge in the middle and this pair of two simplices. So these edges, which I've represented with an equal sign, are degenerate edges. For any vertex, you can get a degenerate edge from the structure maps in a cubical set, which we obtain from the maps in the simplex category delta. Sorry, I said cubical set there, I meant simplicial set. The cubical stuff comes later. So the idea here is that these two simplices witness this diagonal edge having a right inverse and a left inverse. So then a homotopy of maps from x to y would be a map from this object j times x into y. And using this concept of homotopy, we can define what we call a categorical equivalence of quasi-categories. So again, that's just a map which has a homotopy equivalence, this time defined in the, a map which has a homotopy inverse. So a map going back the other way with homotopies from the composites to the identities, where homotopy is now defined in this sense using this object J. And we can extend this again to a definition of a weak categorical equivalence between arbitrary simplicial sets. So this is a map which induces this should say categorical equivalence on mapping spaces into quasi-categories. Right, so this stuff about simplicial sets is all very well established. And another model for homotopy theory, which has been attracting a lot of interest lately, is the category of cubical sets. So these are defined in a similar way as presheaves on a certain indexing category. So now I'll talk a bit about what cubical sets are. So they're presheaves on what we call the box category. That's a category whose objects are the posets 1 to the n for n greater than or equal to 0. So all the powers of this poset 0 less than or equal to 1. And there are various different definitions of the box category, but in general, the morphisms will be some subset of the order preserving maps between these posets, not necessarily all order preserving maps. So when we take presheaves on this category, we think of these cubical sets as consisting of collections of cubes in all different dimensions, which are joined together along faces. And so the representable presheaves here give us what we call the standard cubes, which we can see here we've got a 0 cube, a 1 cube, a 2 and a 3 cube, and of course we have them in arbitrarily high dimensions, and each of these have their faces also part of that cubical set. Right, so as I said, there are various different definitions of the box category for different choices of maps. So in this project that we've been doing, the maps in the box category are generated by 3 specific classes. So on the one hand, we've got face maps and degeneracy maps. So the face maps, which are indicated here in blue for this low dimensional example, are those which embed a cube as a face of some cube in a higher dimension. So here we've got these, this are not 1 cube to the 2 cube that embedded as either this face or this face here. And of course, there would be 2 others for the other 2 faces of the 2 cube. And then we've also got the degeneracy maps, which are the projections, because we define these things as products of poset 1. So these projections we think of as mapping a higher dimensional cube down to a lower dimensional one by sort of flattening it along one particular dimension. And then we also work with what we call connection maps in the box category. So these are maps on these posets which go from a higher dimension to a lower dimension by taking the maximum of 2 adjacent coordinates. So there's only one connection from the 2 cube down to the 1 cube. And so this sends this initial vertex, which we would write as 0, 0, to vertex 0 in the 1 cube. And these top 3 all get sent to vertex 1, because we would think of these as 0, 1, 1, 0, and 1, 1. Right, so when we were dealing with simplicial sets, we defined homotopies using the Cartesian product. Now, unfortunately, the Cartesian product for cubical sets is not quite as well behaved as we might like it to be. For instance, if we take a product of a pair of cubes, we would like to get a cube of this whose dimension is the sum of their 2 dimensions, like a product of 2 1 cubes. We would expect to be a 2 cube. But for this particular version of the box category, that doesn't hold. So if we take box 1 times box 1, that's not equal to box 2. One way to see that is that box 2 won't have any symmetry, like it won't have any non-identity automorphisms, because there aren't any in the box category. Excuse me. And on the other hand, this Cartesian product will have a non-identity automorphism which flips the two factors. So what we do instead is we work with what we call the geometric product of cubical sets. So this is a kind of product that we define by con extension. So we have this map from product of the box category with itself into cubical sets, where we send the pair 1 to the m and 1 to the n to the representable standard m plus n cube. And we take a con extension of that along the product of the Yoneda embedding with itself to get this map defined on an arbitrary pair of cubical sets. And this is much more behaved. In particular, if we take the geometric product of box m with box n, we do get box m plus n just because of the way that we defined this thing initially. Right, so one model structure which has been previously established on the category of cubical sets is what's called the Grothendieck model structure. So in this, the cofibrations are monomorphisms, just as in the previous examples we saw for simplicial sets. The fibrant objects here are what we call cubical con-complexes, which again represent infinity groupoids, and the weak equivalences, weak homotopy equivalences. So what it means for a cubical set to be a cubical con-complex is that we have fillers in that set for all open boxes. So these open boxes are certain cubical sets, which are defined in a way that's similar to how horns were defined for simplicial sets. So to get the nk epsilon open box, we take the standard n cube and take the subcomplex of that, which lacks the interior and the specific face k epsilon, because this is fewer parameterized, as we see here, for epsilon either 0 or 1 and k in between 1 and n. So this is really just the cubical analog of the definition of a con-complex as a simplicial set. And so our concept of homotopy between cubical sets in this Grothendieck model structure is defined using the geometric product rather than the Cartesian product, and using box 1, the standard 1 cube, as the interval object. So a homotopy of maps from X to Y is a map from box 1, tensor X to Y. And then we do the same sort of setup to define homotopy equivalences. So these are maps that have homotopy inverses, maps between complexes, that is, which have homotopy inverses in terms of this particular concept of homotopy. And then we can define weak homotopy equivalences by taking some kind of cubical mapping spaces. So an arbitrary map between cubical sets would be a weak homotopy equivalence if it induces homotopy equivalences on mapping spaces into cubical complexes. All right, so this model structure, this Grothendieck model structure on cubical sets certainly resembles the structure on simplicial sets in a lot of ways. So we might expect them to be equivalent, specifically Quillen equivalent, using a well, in the sense in which I defined Quillen equivalence earlier. And they are, so the functor, which gives us that Quillen equivalence, is what we call triangulation. So this is a functor from cubical sets to simplicial sets, which we define by a con extension. What we do is we send each of these posets 1 to the n to the object box 1, or sorry, delta 1 to the n, that particular simplicial set, which is kind of the natural idea of an n-dimensional cube as a simplicial set. And we take the con extension of that along the Oneda embedding to get this functor t from C set to S set. Now the idea intuitively here, the way we think of this triangulation functor is as taking the cubes in a cubical set and sort of breaking them up into simplices in order to obtain a simplicial set. So that's illustrated right here for a 2 cube. You can see we take a 2 cube and we break it up into a pair of 2 simplices. Now this functor has a right adjoint going back from simplicial sets to cubical sets. So this takes a simplicial set X to a cubical set UX, whose n cubes are maps from this object delta 1 to the n into X. And it was shown by Szynski that this triangulation functor gives a Quillen equivalence between the Grothendieck model structure on cubical sets and the Quillen model structure on simplicial sets. So the goal of this project, which we've been working on, is to essentially do something like that for the Joyal model structure. So to obtain a model structure on cubical sets, which would be Quillen equivalent to the Joyal model structure on simplicial sets via the triangulation functor, and which would be sort of naturally analogous to the Joyal model structure in the same kind of way. But you'll recall that in the definition of the Joyal model structure, we defined quasi-categories using this concept of an inner horn. So if we were to come up with a similar definition of a quasi-category in cubical sets, like a cubical quasi-category, we would need to have some notion of an inner open box for them to have the lifting property against. And it's maybe not as immediately obvious what that should be. Like if you look at all of these 2-dimensional open boxes here, there's none that we can immediately say should represent a composable pair of edges, for instance. So the way that we resolve this issue is we define the concept of the critical edge of an open box, and we say that an inner open box is one for which the critical edge is degenerate. So you can see here that we've picked out the critical edges of all of these different open boxes, and we would require them to be degenerate. And we can generalize this idea of the critical edge to higher dimensions to speak of an inner open box of any given dimension. So I'll go through an example of this to see exactly how this works. So we define a cubical quasi-category then to be a cubical set which has the right lifting property against inner open box fillings. And we can see how this allows us to compose edges. So if we have a pair of edges that we would like to be able to compose in a cubical set X, like say F and G, as I've indicated them here on this diagram, then we can sort of complete this to an open box by adding the degenerate edge at the vertex Z right here. So this gives us a map from the, in this case, the 2, 2, 0 open box into X, for which the critical edge is this, this edge over here, which is degenerate. So this is an inner open box. And so this diagram that you see here will have a lift. So there's so we can extend this map to a map from the standard 2 cube into X. So in particular, that gives us this edge here from X to Z. And then the interior of this 2 cube, we think of as witnessing this edge GF as a composite of F followed by G. Right, so the main theorem that I'll be discussing today, this theorem that we've proven in our paper, is that there is a model structure on the category of cubical sets for which the cofibrations are monomorphisms. The fibrant objects are these cubical quasi-categories, meaning cubical sets having the right lifting property with respect to inner open boxes. And the weak equivalences are what we call weak categorical equivalences. So to explain what these weak categorical equivalences are, once again, we'll define an appropriate concept of homotopy. So just like how we had that interval object for the Joyal model structure that represented an invertible edge, we have something similar here. So this middle edge is supposed to be invertible, and these other two edges are its left and right inverses. And these 2 cubes witness the relevant compositions there. And so then a homotopy of maps from X to Y would be a map from this object K, tensor X, so the geometric product of K with X, into Y, which has whatever restrictions we need at the endpoints. And so we can define categorical equivalence in terms of this concept of homotopy as maps that have homotopy inverses with respect to this, this definition of homotopy. And we can define a weak categorical equivalence between cubical sets to be a map which induces categorical equivalences. Again, there's a typo here. This should say categorical equivalences on mapping spaces into cubical quasi-categories. All right, so one thing that we can do with this model structure, one way that we can generalize familiar concepts from one category theory into the context of these cubical quasi-categories is we can prove an analog of the fundamental theorem of category theory. So you'll recall that a functor between one categories is an equivalence of categories if it's full, faithful, and essentially surjective. So our analog of that is, well, in a cubical quasi-category, we can define a concept of a mapping space between 2 vertices. So a map of cubical quasi-categories is a categorical equivalence if and only if, first of all, it induces a homotopy equivalence on each of these mapping spaces between vertices. So these will be cubical con-complexes. So we're dealing with homotopy equivalence in the Grothendieck model structure. And it should be essentially surjective on vertices, meaning that any vertex of Y is connected to one which is in the image of this map via an invertible edge, meaning an edge that factors through that interval object K. So this is our definition of the mapping space. Essentially, the n cubes in the mapping space from X to Y are n+1 cubes of X for which certain specified faces are degeneracies of these vertices, X and Y. Now this is analogous to a similar result for quasi-categories in the simplicial sense, which, for instance, you can find in Lurie's work in higher topos theory. But the definitions that we have for this cubical mapping space is a bit simpler and easier to work with than these left and right mapping spaces that we look at with simplicial sets. So this cubical model of the infinity 1 categories kind of gives us a simpler proof of this classic result. So much like what Szynski did with the Grothendieck and Quillen model structures, we'd like to show that the triangulation functor and its right adjoint form a Quillen equivalence between the Joyal model structure on simplicial sets and the cubical Joyal model structure on cubical sets. And we do that in the paper. So it's relatively easy to show that this is a Quillen adjunction. Unfortunately, it's a little more difficult to directly show that that this is a Quillen equivalence, like triangulation and its right adjoint are not always the easiest functors to work with, at least directly. So what we do instead is we have this other adjunction, Q and integral, where in this case the left adjoint is from simplicial to cubical sets, and the right adjoint integral goes back the other way. So we first show that this is a Quillen equivalence, and then we use that fact to obtain the result that triangulation and its right adjoint form a Quillen equivalence by showing that the derived functors of these two left adjoints are actually inverse equivalences of categories. So I'll talk a bit about this functor Q and how we define that. So we define certain quotients of the standard cubes to be the image of this functor on the standard simplices. So we have Q0, that's just exactly the same thing as box 0, it's just a vertex. And then Q1, again, is just box 1, just an edge. Now Q2 is a certain quotient of the standard 2 cube, where we take this edge on the right here and quotient that down to a single vertex. So you can see that in doing this, we obtain something which really resembles a 2 simplex. Likewise, Q3, we obtain from the 3 cube by quotienting this face over here down to a vertex and quotienting this this other face to an edge. And in doing that, we obtain something which resembles a 3 simplex. So we have a certain combinatorial formula then, which we can use to obtain a family of quotients of the n simplices, which form a cosimplicial object in the category of cubical sets, meaning a functor from this category delta into C set. Now, in order to define the action of this functor, oh, sorry, I moused over something I shouldn't have there. In order to define the action of this functor on all of the maps in the simplex category, we need to use connections. Connections are important here. So for instance, I mean, I'll show you how this functor acts on all the maps in delta. So we have these maps that include a simplex as a face of a higher dimensional simplex, and those we can obtain from the maps that include cube as a face of a higher dimensional cube. So for instance, if we're including an edge into a 2 simplex, including Q1 into Q2, that is, we obtain these from certain face maps between box 1 and box 2, which descend to this quotient. And then we also have degeneracy maps in the simplex category, meaning surjective maps from a higher dimensional simplex down to a lower one. So this one, for instance, where we map these 2 vertices of the triangle down to this vertex of the 2 cube down onto the 1 cube. But this particular degeneracy, where we send these vertices to this one, we have to use a connection to get. You can see here that we're sending these 3 vertices, 2 of which have already been identified, to this 1 vertex of the 1 cube down here, and that we accomplish using a connection. So these objects Qn form a cosimplicial object, meaning a functor from box n to from, I don't know why I said box n there, delta to cubical sets, which sends each poset n to the quotient Qn of the standard n cube. And as we have done in similar cases in the past, we take the con extension of this functor along the Yoneda embedding from delta into simplicial sets. And so we obtain this functor Q from simplicial to cubical sets. And we can show that it has a right adjoint integral, which is given by this formula. So for a cubical set X, integral X is a simplicial set whose n simplices are maps from n into X. Now, this adjunction was studied extensively by Kapulkin, Lindsey, and Wong in that paper of theirs, which I cited at the beginning of the talk. And one of the main things that they showed there was that this adjunction defines a co-reflective inclusion of simplicial sets into cubical sets. So what that means precisely is that this left adjoint functor Q is fully faithful, or equivalently, each component of its unit is an isomorphism. Another thing that they show is that the co-unit of this adjunction is monomorphism. In other words, we can think of Q integral X for any cubical set X as a certain subcomplex of X. And specifically, it's the subcomplex whose n cubes are those which factor through the quotient Qn, which we can think of as sort of the maximal simplicial set contained in the cubical set X. So we can show, and we show in the paper that, that this adjunction, Q and integral, is a Quillen equivalence. And so then we have a natural transformation from the composite of these two left adjoints, from Q followed by T to the identity. And we can show that this is a natural weak categorical equivalence. So each component is a weak categorical equivalence. So then when we pass to the homotopy category, this will actually become a natural isomorphism of the derived functors that we have here. And so then, because we know that the derived functor of Q is an equivalence of categories, we obtain from that that the derived functor of T is an equivalence of categories. So that covers all of the main stuff that I had been planning on talking about today. It looks like I've got a little bit of time, so maybe I'll just briefly touch on some of the other results we have in this paper. So we actually have two more model structures, two more cubical models of infinity 1 categories, which I didn't discuss today. So there's a model structure that we've developed on the category of marked cubical sets. Those are cubical sets in which certain edges are distinguished as marked edges, and those sort of represent equivalences in a homotopy sense. Right, and then we also have the category of structurally marked cubical sets, which are cubical sets where edges can have more than one marking. So we actually, in the paper, develop these model structures first and then use those to obtain our model structure on cubical sets. We develop a theory of what we call cones in cubical sets, which we use in order to prove that Q and the integral form a Quillen equivalence. So these are like, well, I won't get into the technical details of that construction, but Q is sort of developed, well, it's closely related to the adjunction Q and integral. And using the same argument that we use for the, to show that triangulation and its right adjoint form a Quillen equivalence between the Joyal and Cubical Joyal model structures, we actually also get a new proof that it's a Quillen equivalence between the Quillen and Grothendieck model structures, so a new proof of that result of Szynski. It's really just a very quick adaptation of the same argument. Everything just works out the same way. And we have a new proof of the fundamental theorem for quasi-categories. So as I mentioned, we've got a proof of that in this cubical context, which is simpler than the traditional proof in the simplicial setting. And then we can actually just use this right adjoint of triangulation to transfer the proof from the cubical to the simplicial setting. And that is everything that I had to discuss today.
All right, thank you very much. I'll just say flip one slide earlier, maybe. It's not the best tool. Yeah, thanks. And okay. So let's have silent applause to thank Brandon for this great talk. All right, and now we have some time for questions. So feel free to unmute your microphone and ask a question. Some people are typing clap, clap. So that, I guess, is silent. Okay.
I would have a question.
Go for it.
Yes.
So, I mean, I was wondering how I mean, you've chosen one very particular cube category. So how sensitive is this to that particular choice? So, I mean, would similar methods also work for some of the other cube categories that people work with in homotopy type theory?
We expect it to work for some, but not all. So one thing is we did need connections in order to define the cosimplicial object Q. So that is something that might go wrong if we tried to remove connections from the cube category. We do expect it to work for so there's another kind of choice of the cube category that people work with where you have not only max connections, but also min connections that take the minimum of 2 adjacent coordinates. And we expect this to work in that setting as well. That's something that we're currently looking into. If you were to add many maps beyond connections, it's possible that some difficulties could come up because the proof that Q and integral form a Quillen equivalence is very combinatorial and kind of relies pretty heavily on like a specific description of the maps in the box category and a specific sort of unique factorization that you can get, like factoring every map into faces, degeneracies, and connections. So there would be at least a lot more stuff to check there if we wanted to incorporate more maps beyond that, like say symmetries or diagonals.
Okay, yeah, thank you.
I think Martin Highland has a question.
Yeah, could I ask this in terms of the this quotient Q? I mean, you're quotienting a cube down to something or other, and in principle, just geometrically, there are lots of ways to do that. Is the way you do it forced on you by the choice of connection?
Oh, that's a good question. Let me think about that for a second. I would say that to some extent it is. So we do, like when we define this, one of the image of some of the degeneracy maps between the different simplices is given by connections between the cubes. So for that reason, we do kind of need to make some of our choices that we do in defining this quotient in order for this to be compatible with our choice of connections. I believe there may be, I mean, I don't want to say anything too strong here. Right.
I don't want to don't force yourself to decide.
Right.
But I mean, it just occurs to me that if you have both connections, maybe you then have two choices for Q so that you would get an interestingly rich structure.
Yeah, so I think the way it works out combinatorially is there are essentially 4 kinds of choices that we can make in defining Q because the face maps, like the faces of a cube, are indexed by 2 different variables, right? We have like a face, like there's a K epsilon face for K0 and epsilon either 0 or 1. So, well, I can define in Q2, for instance, we could in principle choose any of these 4 faces of the 2 cubed quotient down to a vertex. So I think wanting it to be compatible with this particular kind of connection reduces that to 2 possible choices. We could quotient either this face or this one.
So maybe I'll add that this, I mean, Q is really the straightening functor. So Lurie has this construction of straightening and straightening, and Q and integral are just, so integral comes from the category of elements. And so you can do it covariantly and contravariantly, the category of elements for covariant functors and contravariant. And max connections correspond to covariant and min connections correspond to contravariant.
Right, thanks.
All right, we still have some time for questions, comments, and insults, or anything that's on your mind.
Insults are always welcome.
We can check President Trump's Twitter feed if you want those.
I've always wondered how he felt about cubicle sets. When Peter was talking about, what was it? Headless roll, I thought of US response to COVID. Right, final call for questions. All right, well, there are, I think, no more questions. So let's thank Brandon again for the talk. And okay, and we're gonna close for the day. So thanks everyone, and we'll see you tomorrow at 10:30 Eastern.